last thing I did this morning. All right, so here's what I want you to get out of the lab that we started today, which we were going to, or yesterday, which we're going to finish up today. So one of the things that they had to figure out was that how do reactions indicate what's happening on an atomic level? So if you look at what happened, you all took calcium and you added that to water. So our next big thing, once we get past this, is writing and balancing chemical equations. So a chemical equation basically tells you, hey, this is what's happening. So you took calcium and you dropped that into water. So here's the short version of what happened. So here's your water molecule, 1 oxygen, 2 hydrogens. And the calcium comes along and it basically kicks out one of those hydrogens. Okay, so it comes along and says, boom, you're out. Now, hydrogen, like most gases that are in the elemental form, hydrogen, nitrogen, oxygen, fluorine, bromine, we'll talk about those, are known as diatomics, which means that they don't exist by themselves. So what happens is that as soon as this hydrogen gets kicked out, okay, you form a substance called calcium hydroxide, which is CaOH2. And the reason that it's CaOH2 is that calcium has a charge of 2+. And the reason calcium has a charge of 2+ is because it's in that second column. So it has 2 outer shell electrons. So it gets rid of those. This hydroxide group, if you look on that periodic table that I gave you, it's called an anion. It has a charge of 1-. So basically, that hydroxide here has a deficiency of 1 electron. The calcium wants to give up that. So what happens is the calcium then, because it wants to lose 2 electrons, each hydroxide can only take in 1 electron, so it's like a match game. So that hydroxide has to take, that's why you have to have 2 hydroxides, because each one can only take in 1 electron. Oh, okay, it's a match made in heaven. So then you also get out of that hydrogen gas. So you all saw all these bubbles form, like some of you had actually like overflowed the top of the test tube, okay? Now, out of this, and some of you can attest to this, you also got a tremendous amount of heat, okay? That test tube got really, 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 really hot, okay? So out of a byproduct of this, Mother Nature goes, all right, and you all have talked about this in terms of a reaction. Basically, you said, here was the initial energy state of the calcium and the hydroxide, okay? You mixed them together, which was that activation energy, and then you ended up way down here. So these products of calcium hydroxide and hydrogen ended up at a much, much, much lower energy state than where you started, which is why it got so hot, okay? It's like, oh, that energy had to go somewhere, so that energy was being released because of the fact that you were forming all of these new bonds, and in the formation of these bonds, energy got released. So then you did the same thing with magnesium, same thing with aluminum. Now, when you did magnesium in the water, okay, was there a reaction? Grace, when you did magnesium in the water, was there a reaction?
It turned a little bit greener, but there was no really bubbles.
Okay, so might have been a reaction, right? So if it was, it wasn't near as vigorous as the calcium was. So the calcium's going, wow, that was really cool, gave off these electrons. Magnesium, okay, might have formed a little bit of magnesium hydroxide and hydrogen gas. Now, what happened when you put in the aluminum? Did the aluminum react at all? No, okay? So here's the deal. So the aluminum and water, we got no reaction, okay? RXN is a shortcut of way of writing out the word reaction. It's just RXN. So here's the deal. So think this through. If you were designing cans to hold water, peace out, Girl Scout. If you're designing cans to hold water, you have 3 materials you can build them out of. You could build them out of calcium, you could build them out of magnesium, you could build them out of aluminum. Which one are you going to pick? Aluminum. Why? Yeah, as soon as that, oh, we're going to put water in calcium cans. That's cool, right? Not really, because as soon as the calcium hits the water, the can disappears. Okay? You get a lot of heat and bad things can happen. So this is why aluminum is used in cans, okay? Because you have three advantages of aluminum. Number one, it's abundant. Number two, it's malleable, okay? It's easily bent. And it's not very dense, okay? Aluminum is a low density metal. So you have a whole bunch of things going for you. And most importantly, it doesn't react with the stuff that you're going to put inside the can, okay? So if you're out prospecting in Colorado, okay, there's lots of minerals, you're not going to look down and find a chunk of calcium in water. Okay, it's not there. Calcium will exist as an ion, so if you all have well water, okay, and if you get like the white scaly deposit, like on glass or in your showers and stuff, that's calcium, because calcium dissolves very easily in water. So if you clean your shower, you'll talk about calcium deposits, because calcium exists in water as an ion. Water evaporates, the ions, those calcium ions are left behind. That's that scaly white stuff that shows up on the shower. Okay, so when metals react, okay, and this is one of the key things that we're going to begin to, I'm just going to lay the groundwork now. When you had that chunk of calcium, okay, it existed as a neutral atom. So, Grace, what's the atomic number of calcium? Or you can just look behind you. Left side. 20. Okay? So the atomic number of calcium is 20, which means it has 20 protons and it has 20 electrons. Okay? Now, here's the whole deal. If I were to ask you to write the electron configuration for calcium, you would say, oh, that's 1s2, 2s2, 2p6, so there's 10. Then we got 3s2, 3p6, and then 4s2. Okay, so let me show you a little shortcut that you can do. Okay. Grace, just because I don't have my glasses on. So, find calcium. Now, go to the row above calcium and go to the far right side and tell me the noble gas that's in the row above calcium. Argon. So, this arrangement right here is argon. Okay, that's a noble gas. And all the gases want to be like the noble, or all the elements want to be like the noble gases. So basically what you can do is a shortcut way of writing your electron configurations is that you put a noble gas core, okay, like argon, for example. So you have argon, and then you have 4s2. So here's the deal with calcium. Calcium's sitting there going, I got 20 protons, I got 20 electrons. It's cool, right? So then what's going to happen is that calcium sits there and goes, I want to be like argon, okay? So to do that, it's got to get rid of those two outer shell electrons. Now, let's look at this in terms of Coulombic attractions. So calcium is out there in 4s2. Now, Grace, follow the same pattern. Find magnesium. What's the noble gas above magnesium in that row above it? Neon. So if you look at neon, and then 3s2, so here's the deal. So calcium wants to lose electrons that are out there in that fourth energy level, okay? Magnesium wants to lose electrons that are out there in that third energy level, okay? So they're both out there in the outer regions, but calciums are further away. So because those electrons are further away, Ella, what do you know about the attractive force between the nucleus of calcium and those 4s versus magnesium and those 3s? Which one's going to have the greater attraction to its electrons? Magnesium or calcium?
Magnesium.
Perfect. Why?
So it's closer to the top?
Yeah, well, it's closer. The electrons are closer to the nucleus. Okay? So the atomic radius of magnesium is smaller than the atomic radius of calcium. So if you go down, remember, if you go down a group, and there are certain things you have to begin to know without fail, without hesitation, without any thought at all. One of the most important trends, because it drives about everything else, is atomic radius. Okay? So as you go down a period, okay? So you go down a group, atomic radius gets bigger. Okay? Gets bigger and bigger and bigger, because it's like layers of an onion, and you're getting bigger and bigger and bigger and bigger and bigger. So that's like you're building an onion. So as you go down, atomic radius gets bigger. Now, adding, as you increase the atomic radius, what happens to the attractive force between the nucleus and the electrons? So here's Eddie the electron, okay? As Eddie the electron gets further from the nucleus, what happens to the attractive force? Decreases. So because of that, the attractive force as you go down becomes smaller. Okay? So there's two things that are happening. The atomic radius is getting bigger, so the attractive force is getting smaller, so those electrons are easier to get, or easier to be given off. Now, as you go across, and this is the one that's counterintuitive, trust me, this is the one that gets missed the most. As you go across, everybody wants to say, oh, atomic radius should get bigger because I'm putting more electrons in there. But here's what's happening. As you go across, you're increasing the number of protons in the nucleus as you go across. So, as you go across, that Eddie the electron is being attracted to more and more and more protons. So Eddie the electron, as it's feeling that attractive force between more and more and more electrons, they pull in tighter and tighter and tighter. So as you go across, the atomic radius is actually getting smaller. Everybody intuitively says, oh, but you're adding more electrons, Burke. Why doesn't it get bigger? You put more electrons in there. It should get bigger. The reason it doesn't, and this is one of the most important things, you listen to me, is that electron feels, each Eddie the electron feels an attractive pull towards that nucleus, okay? Because it pull whatever happens with the other one doesn't matter. This is all about Eddie, okay? So Eddie the electron, as you go across, they're putting more and more and more protons in that nucleus. As that's happening, Eddie the electron's going, man, I'm pulled more and more and more towards that nucleus. As that happens, it gets sucked in closer and closer and closer and closer and closer. So if you look at what just happened with magnesium and calcium, calcium was much more reactive because those two electrons in calcium were way out there in the outer regions. So what happens is that calcium then could give up those electrons easier. As that calcium gave up the electrons easier, that reaction took place much more vigorously. Okay? So in this situation, we could look at this and go, we ask ourselves, okay, magnesium, calcium. What physically took place that calcium reacted so much more vigorously than magnesium? Because they're identical. They both have two valence electrons. Okay, that's what they have that in common. So there has to be something in the difference about how they give up their electrons. And the difference being is that those calcium electrons are further away, they're not held as tightly, they give up those electrons, that's what starts that reaction. So aluminum is sitting there going, now you find aluminum, so let's look at aluminum, okay? So aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. So when you look on a periodic table, aluminum is right there, okay? So aluminum has 3 valence electrons. These 3 right there. But because it's further to the right on the periodic table, aluminum has a smaller atomic radius. So aluminum's sitting there going, man, I got these 3 electrons, okay? Really don't want to give those up. So that's why aluminum basically goes up to the water, and the water says, hey, you want to start a chemical reaction? The aluminum basically says, no, I'm good, thanks. We're just gonna stay here. We're just gonna chill out, okay? Not gonna react with you. I appreciate the fact that you want to take my electrons, but I'm gonna politely decline. Because Mother Nature's a lazy prima donna. So Mother Nature goes, it's more stable and it's a lower energy state for me not to react than to react. Whereas calcium, Mother Nature goes, man, get rid of those electrons. They're out of here. Outie, boom, okay? Because Mother Nature wants to end up at a lower energy state. So she does that by giving off those electrons and starting that chemical reaction. Magnesium does the same thing, but magnesium's like, maybe yes, maybe no. We're not so keen on the idea because I kind of like my electrons. Calcium's out of here going, boom, they're out. So calcium, if you make the analogy, imagine that calcium is like you guys going out on a date. And you have to take your annoying twin little brothers, okay, out on the date with you, okay? And they're a long way from you, and you really don't like them anyway. So somebody comes along and says, hey, can I have your twins? Sure, get them out, gone, don't care about it, right? Because you're going to be more stable once you get rid of the electron. So here's your overriding theme. Reactions take place to increase stability. So when you see a reaction take place, what you end up with is going to be more stable, going to be at a lower energy state than it was before. Okay, that's Mother Nature's overriding theme. So if you keep that in mind, if you look at all the reactions that we're going to do, if you see something happening, it's because Mother Nature gains something from it. If Mother Nature doesn't gain something from it, it doesn't happen. Okay, so if you keep that overarching theme in mind, that's going to be important. Now, look at what happened with the hydrochloric acid, okay? So you dumped calcium into hydrochloric acid, okay? Hydrochloric acid is HCl. Now, what happens here is that, start with this idea. And it's simple, but it's going to be very profound, okay? Y'all had hydrochloric acid. In what form was hydrochloric acid? Was it a liquid? Was it a solid? Was it a gas? It's liquid, right? Poured it out. Look clear. All the solutions that y'all messed with yesterday were clear, right? So what happened is that hydrochloric acid actually exists as hydronium ions, which is basically, here's a typical hydrogen atom, one nucleus with one electron going around. So basically, it's lost an electron. So this is basically a single proton. So when you talk about H+, okay, it's a proton because it's lost an electron. That's all it is. Chlorine over here, and this is why you have to learn so much about atomic structure. Chlorine has 7 valence electrons because it's a halogen, okay? What's the magic number for electrons? Chlorine has 7. How many does it want? What's the magic number for electrons? 8. It has 7. How many does it want? It wants 1 more. So chlorine wants to take in an electron. So chlorine has a charge of 1 minus because it's gained an electron. So what's happening is that on an atomic level, here's your, or you can make it color coded. So here's a water molecule. Water is going to play a key part in today's story. Plays a key role in a lot of stories. Okay, so here's a water molecule. Here's your hydrogen end, here's your oxygen end. Which end has the negative charge, which end has the positive charge? Luke?
The oxygen has the
Rhymes with negative.
negative charge.
Okay, now here's the reason why. Look at oxygen. You find oxygen on the periodic table, oxygen has 6 outer shell electrons. How many does it? It has 6. How many does it want? 8. It's going to gain 2. Hydrogen has proton, right? 1 electron. So each hydrogen gives an electron to the oxygen. It's okay, well that's cool. That's why it's H2O, because oxygen has 6 valence electrons and it gains 2 more. Okay, cool. So on this water molecule, you've got the negative end up here, you got the positive end up here. So this is the chlorine, right? So the chlorine, which has a negative charge, is attracted to the positive end of the water molecule. And imagine this is the other one, this is the proton, and it's attracted to the oxygen end. So basically, what happens is this. You drop that calcium in there. Here's the water molecule, okay? And the proton is on this end, and the chlorine is attracted to this end, okay? It's existing as a liquid, okay? It's actually attached to the water molecules. So you drop in that calcium, and the calcium reacts with the hydrochloric acid, and basically what happens, again, calcium is trying to get rid of its electrons because it's going to be more stable. You have the twins with you, and you're out on a date. You want to get rid of the twins because it's going to be more fun, right? So the calcium says, okay, hey, I want to give up these electrons. So here's what I want you to think through. This is H+, and this is Cl1-. Calcium wants to get rid of negatively charged electrons, okay? So here's what I want you to think through. Is calcium going to give up those electrons to the hydrogen, or is it going to give up the electrons to the chlorine? Which one? Emma. Are those electrons going to be more attracted to the positively charged hydrogen or the negatively charged chlorine? Opposite charges. Remember that. What do opposite charges do?
It's the hydrogen.
Fantastic. So basically, the hydrogen comes along, and it comes up to the calcium. Hydrogen says, "Hey, I'm positively charged. I'm upbeat. I'm positive." Okay. It comes up to the calcium, and it says, "Hey, I'm positively charged. I see you got some electrons. You want to get rid of them?" Calcium goes, "Score, dude. Okay. I could care less about them. Take them." Okay. So what happens is that it gives up those electrons to the hydrogen. So as soon as that proton, that hydrogen, gains an electron, it goes back to being hydrogen. You say, oh, now I'm balanced again. So now I have a proton and an electron. So what happens, though, the calcium, though, now becomes positively charged. So it now becomes attracted to the negatively charged chlorine. So this is a win-win for everybody. Hydrogen gets its electrons back, then it forms hydrogen gas. The calcium then bonds with the chlorine. It's a score, okay? So the calcium has lost its electrons, so it's happy. The chlorine gains its electrons because now it has a negative charge. So look at this. So out of this reaction, you get calcium chloride and hydrogen gas, okay? And again, the reason that that's Cl2+ is because each chlorine needs one electron. Oh, but calcium gives up two. So calcium gives one electron to a chlorine, it gives the other electron to another chlorine, it's matchmade in heaven, everybody's happy. So that little bubbles that you saw forming, oh, that was the reaction that was forming hydrogen gas. Now, y'all measured the temperature. What happened to the temperature on that one? What happened to the temperature? Temperature increase or decrease? Decrease. Or the temperature went up a lot. So that means that Mother Nature got rid of that energy. It gave off that energy in the form of heat. Now, when you did magnesium, guess what? It's the exact same reaction. You got magnesium chloride and hydrogen gas. Okay? It's the exact same reaction. Now, which reaction took place more vigorously? The calcium and the hydrochloric acid or the magnesium and the hydrochloric acid? Which one took place more vigorously? Parker?
The calcium.
Yeah. Guess what? Same idea. You see no pun intended, but do you see the periodic trend? Calcium, again, it's the exact same idea. Calcium was giving up its electrons. It gave up those electrons more easily. The reaction took place more vigorously. Okay? Most situations you form hydrogen gas. What happened when you put the aluminum in the hydrochloric acid? Grace, what happened when you dumped that aluminum in that hydrochloric acid? Yeah, nothing. Because the aluminum sits there and goes, I'm cool. Okay? I've got my electrons, I'm going to hold on to them. Okay? Not going to give them up. So that's the cool thing about what you just saw in terms of that reaction. So Mother Nature allows reactions to happen because you gain something from it, okay? And it's usually the transfer of electrons. Now, what you're gonna do today, okay, here's gonna be the next part. So, you're gonna do that backside today. So here's what's gonna happen here. You're gonna take, like, for example, I don't know, sodium sulfate, and you're gonna react that with barium chloride. Okay, so on your sheet, it's like a mix and match kind of thing. So here's what's gonna be important here, okay? Again, this is where water plays a key role. All of these solutions that you start with are going to be liquids. So what's happening here is that this is existing as a sodium ion, a sulfate ion, a barium ion, and a chloride ion. And all of these are attracted to water molecules. So the sodium ion is attracted to the water, the sulfate is attracted to the hydrogen end. Here's another water molecule, okay? Barium is, because that's positively charged, is going to be attracted to the oxygen end, and chlorine is going to be attracted to this. So these exist because it's a tug of war, okay? So basically the sodium comes along and says, when we mix these up, sodium sulfate is a white powder, okay? So sodium sulfate, you can go into the storeroom. I can tell Luke, hey, go get me a bottle of sodium sulfate, okay? Goes in, he finds that it's a white powder. We pour that into the water itself. It's soluble, it dissolves, just like salt or sugar dissolves in water. Sodium sulfate dissolves in water, and here's the reason why. Because the sodium's bond with the water and the sulfate's bonds with the water are stronger than the bond that it has with itself, okay? And that's why it dissolves, because it's a tug of war. The water comes along and says, yo, sodium, why don't you come and hang out with us? Sodium says, I kind of like the sulfate. The water goes, come on, I'm cool, I'm water. Sodium says, okay, all right. So it breaks the bond between the sodium and the sulfate. Same thing happens with barium chloride. Barium chloride, you go in there and you can find a bottle of it. It's a powder. You put it in with water, boom, it dissolves. This is how we make these chemicals. So here's what's going to happen on an atomic level. When you're going to mix these together, you have sodium ions, you have sulfate ions, you have barium ions, and you have chloride ions. So this is like mix and match, okay? So the sodium is going to bond with chlorine because they're oppositely charged. It's going, oh, this is kind of cool. It's like a dance. Hey, yo, sodium, chlorine, let's talk, okay? Because they're oppositely charged. They're going to attract each other. The barium is going to become attracted to the sulfate because they're oppositely charged, okay? So here's the deal. If you form a precipitate is that chunky stuff that you'll see. If it forms a precipitate, it's because this attraction here is stronger than the attraction for the water molecules. So basically, you're reversing the process, you're reversing the dissolving process. So what you'll see is if you form a precipitate, then we'll spend a lot of time talking about precipitates. If you form a precipitate, because the bond between the ions to each other is stronger than the bond that it has with the water molecules. So the barium and sulfate, they see each other, okay? And it's like love, true love. If you've ever seen a movie called Princess Bride. It's an old movie, but it's a classic if you haven't seen it. And so basically the barium and sulfate, they see each other and it's like, oh man, I've been waiting for you all my life, okay? So they form this bond. So as soon as they form this bond, they stop existing as ions in the solution. And once it forms that bond, then they kind of settle out. They leave the dance party as ions, they chill out, okay? So imagine that you have this, you're at homecoming dance, and people are out there, right? They're dancing around, everybody's kind of doing their own thing, right? And then all of a sudden, this couple sees each other and is like, oh man, that's cool. Hey, let's go hang out. So they leave the dance floor and they go sit at tables over to the other side, and they're precipitating out. So when you see a precipitate, you've gone from this ionic dance party where everybody's dancing around, existing as ions, and go, oh man, I found my soulmate, okay? But once you find your soulmate, you're not allowed to be out on the dance floor anymore. You've got to go hang out. Now, here's the deal. So what you're gonna see is that some of these form a lot of precipitates, some of them don't form very many precipitates at all. But again, go back to this idea. Barium, you'll see, has a very, very strong attraction to things, okay? So anions are drawn to that barium. Oh man, it's cool, right? It's barium, okay? It's a really attractive person. Anions go towards them. Now, the sodium and the chlorine, they're attracted to each other, but guess what? That's not going to form a precipitate because it's salt. Salt dissolves in water. Okay, so the sodium and chlorine are attracted to each other. They're like, whatever, kind of, not so much. We're just friends. Okay, so they're really not going to do much. They're just going to hang out. They're still going to exist as ions. But the barium and the sulfate, they go, bam, barium, sulfate, boom. Okay, they're going to stick together. They're going to form a precipitate. That's what's going to settle out of that solution. Got the idea? And I know it was kind of like drinking out of a fire hydrant. But here's what I want you to keep in mind. When you see something forms a precipitate, okay, I want you to have this visual. They're existing as ions. You're going to mix them together, let them go, whoop. And as soon as they form that precipitate, they're going to fall to the bottom of that well plate. So when you see a precipitate, remember you have this visual. Two ions, stick, boom, fall. Okay? That's what makes a precipitate. Now, if you don't form a precipitate, it's because they just run into each other, but they don't stick. Precipitate, stick, boom, fall. Stick, fall, stick, fall. Okay? And the stickier they are, the more likely they are to make a precipitate. Okay? You got that visual. Okay, so here's what we're going to do. Go over there, you're going to fill out this data table. Okay? Then what's going to happen is that Luke is going to come up to Ella and go, Ella, hey, pick one of these: magnesium, calcium, strontium, barium. Okay? So what's going to happen is that Luke is going to take his well plate and he's going to give it to Ella. Okay? And Ella is going to pick one of the four: magnesium, the calcium, strontium, and the barium. Okay? Not the sodium sulfate, not the potassium iodate. She's going to pick one of these four. She's going to take a well plate, and here's going to be this well plate, and she's going to put 5 drops of one of those. Let's say that she picks barium chloride. Okay? So she's going to put 5 drops of barium chloride in each of those 3 wells. She's not going to tell Luke what it is. Okay, this is the whole point. She is not going to tell Luke what it is. She then, after she does that, she's not going to tell Luke what it is. She's going to give that well plate back to Luke. Luke then is going to add sodium carbonate, sodium sulfate, and potassium iodate. He's going to add these 3 to them. So he's going to add those, right? And then he's going to make that observation, what happened. Then he's going to go back to his data table and go, wow, which of those 4 matches this? Okay? That's what's going to happen. So what you want to do when you get to that unknown part, you listen to me very carefully. Okay? Listen to me very carefully. You're going to go to another group. Do not watch what they're doing. Stay with me through the spirit of this lab. They are going to give you that unknown. You are going to get that. Okay? We're good? Okay, let's go do science. So, stop yonder camera, please. Okay, so here's hopefully what you saw when you have that precipitate chart filled out. So let's look at the 2 extremes. When you look at your chart, if you compare the magnesium, the calcium, the strontium, and the barium, okay? So let's look at, first off, what do those cations, the magnesium, calcium, strontium, okay, barium, right? So what do they have in common in terms of where they are on the periodic table? Are they in the same row going across, or are they in the same period going down? Same period. Which period are they in? 2. So here's the simple thing. All of these have a charge of 2 plus, right? And they all have a charge of 2 plus because they all have, if you look on their arrangements, they all have a noble gas core and then something S2. Like magnesium is 3S2. Calcium, strontium, okay? All of these are S2. So all of these have 2 valence electrons that are out there. So what they all have in common is that they want to be like a noble gas. So if you look at magnesium, okay, magnesium wants to lose 2 electrons, so it has the appearance of neon. So let's say, for example, you really like a particular movie star, okay, Tom Cruise, I don't care, pick one, okay? And you go, wow, I want to look just like that movie star, Lady Gaga, if you're into pop, whatever, okay? And you do your hair the same way that they do, and all of these things. You dress with the same clothes, everything, okay? So on the outside, you have that appearance of that particular movie star. But are you actually that person? No, because what's on the inside is what makes you you. So this is basically what the elements want to do. They want to look like a noble gas. They want to gain electrons or lose electrons to look like a noble gas. But they're not actually becoming the noble gas because we don't change the number of protons that are on the inside of the nucleus. Okay? So they can look like it because they're becoming more stable, but they're not actually those elements because you don't change the number of protons that make that up. So, as a trend, let's look at the extremes. Magnesium all the way over to barium. Which one of those two, just comparing magnesium and barium, which one of those two formed the most precipitates? The magnesium or the barium? Barium did, right? Okay? So what that tells us is that barium, and again, you look at what happens to form a precipitate. So here's this barium. It's floating around in the solution. Okay, it's floating around, floating around, floating around. Okay? Barium runs into, like for example, that carbonate. So if you look at carbonate, if you look at that, so when you reacted barium chloride and sodium carbonate, did that form a precipitate? So, Ella, look at your data table. When you reacted barium chloride and sodium carbonate, did that form a precipitate?
And what?
Barium chloride, BaCO2,
Yeah.
and sodium carbonate, which is the Na2CO3.
Yeah.
When you mix those two together, did you form a precipitate?
Yeah.
Yes. Okay. So what happened is that the barium is floating over here. It sees the carbonate, and they go, boink, fall out, make a precipitate. Okay?
So for your encore from Miss Ross.
Okay, thank you.
Thank you.
So when you looked at barium and the sulfate and the Na2SO4, okay, did that form a precipitate? Emma, did that form a precipitate?
Yeah.
Okay, so again, here's the barium, here's the sulfate, boink, boom, fall out. What about the barium and the iodate, which is KiO3? Iodate, it's kind of fun to say. Did that form a precipitate? Yep. So what this means is that this barium is really, really attracted to those other anions. And they form a bond, boom, they fall out. Now the magnesium was attracted to it, but it's like, not so much, okay? How many precipitates did magnesium form? One. Well, and even then, on your dot scale, one dot wasn't much, was it? So it kind of formed a precipitate, but it was only one dot. Okay. So even the even the one that magnesium did form a precipitate with, that's just okay. Okay, not a whole lot. It's like, it made some. barely out of the friend zone, but not much. Whereas the barium's going, hello, boom, boom, we're gonna make it precipitate. So, again, we cannot see what's happening on an atomic level. But what we do is we look at and say, hey, does that make it precipitate? So what that tells us is that barium is reactive. Barium really wants to take in and bond with those anions. The magnesium, not so much, okay? So that's how you want to approach this. Now, let's make sure everybody's cool with the terminology. So in that post-lab question, it says which group 2A element, so when you're talking about group 2A, okay, this is going to be coming down here, right? And so group 1A, I want to make sure everybody's cool with this, that's the alkaline metals. And these are the rare earth. Because they're kind of rare and they come from the earth. Okay? So you have your group 1s. Group 1s have one valence electron. They all have a charge of 1 plus. Group 2A, those have 2 valence electrons. Those all have a charge of 2 plus. Okay? And remember, metals react by losing electrons. Okay? Because that's what they want to do. Because they want to become like noble gases. So then when you get to question number 2 on the back says is which period 3 metal. Now, here's the deal. You're talking about magnesium and aluminum. So periods go across, groups go up and down. Okay? Periods go across, that's one of the first things you have to have. Because if you don't know the terminology, the question doesn't make any sense. So groups go up and down, periods go across. So then, on number 3, it says rank the 3 metals in part A from most to least reactive. So what you want to have on that ranking, okay, from part A, you have the 3 metals. You have the calcium, the magnesium, and the aluminum. You want to rank them in order from most reactive, so in other words, hey, if I put this in with something, boom, that's going to happen fast, to the one that says, not so much, okay? So that you're going to rank those. Now, the heart and soul of this is when you get to question number 4. Question 4 says, write a general statement about the periodic trend in metal activity across a period of the periodic table. So in other words, if you're going to go across, like let's say for example, you have the one where it goes, all right, say for example, you go from sodium to magnesium, aluminum, silicon, cross, and then you're going to go in from potassium, okay, cross like this, right? So here's the reason that we chose these particular elements, is because you can make comparisons going up and down, and you can make comparisons going across. That's why we chose these elements for this lab, okay? So here's the deal. Let's talk about magnesium and calcium. Which one is more reactive between magnesium and calcium? Which one is more reactive between magnesium and calcium? Luke?
Calcium.
Calcium. So going down, calcium is more reactive. Now, going across, you have magnesium and you have aluminum. Which one is more reactive, magnesium or aluminum? Emma?
Magnesium.
Okay, so across, okay, your reactivity becomes smaller. As you go down, the reactivity becomes greater. Okay, so that's one of the most important trends I want you to see. So as you go down, and this is in terms of metals, okay, listen to me very carefully. This is in terms of metals, okay, not non-metals. These are metals that we're talking about. Non-metals are a whole nother beast, okay? Non-metals are a whole nother beast. So, when you get to 6, okay, use your results in part B to deduce the identity of the unknown alkaline earth metal, okay? Explain your reasoning. So what you want to say, and here's what I'm looking for on number 6, because each group had a different unknown. Okay, I obviously know which ones I gave you. But don't think, oh, everybody had the same unknown. Each of you had a different unknown. And again, listen to me. Your unknowns are not the reagents. Your unknowns are not sodium carbonate, sodium sulfate, or potassium iodate. That isn't your choice. Your choices are either magnesium, calcium, strontium, or barium. Okay? So here's what I'm looking for on that. Let's say, for example, you think I gave you calcium. Okay, cool. So you'd say calcium. How did you know that? Okay, you could, if you're using the Grace dot scale, you could say, well, I got 2 dots with sodium carbonate and sodium sulfate and 3 dots with potassium iodide. That matches with the strontium. Okay, so you want to lay out how they reacted with the reagents. Just don't say, oh, it formed a precipitate. Well, that's just too vague. Okay. What type of precipitate? Was it heavy precipitate? Did it not form a precipitate with one particular reagent? Did it form a precipitate with all of the reagents? Okay? That's what you want to lay out. Now, when you get to question number 7, okay, let's talk about ionization energy. So ionization energy is basically a measure, if you consider like these little magnets like this, ionization energy is how much energy I have to put in to pull these apart, okay? Because you're pulling away an electron. So if these were really strong magnets, I'd have to pull really hard to break them apart because the attractive force is so strong. I can pull these apart. It's a little bit of effort, not a whole lot. It isn't like, I've got to try really hard. So first ionization energy is a reflection of how strong the electrons are held. The higher the first ionization energy, the more effort it takes to pull them apart. So if you look at this, you go in calcium, magnesium, potassium, sodium, okay? So of those, which one of those elements listed, you'll notice that potassium has the lowest first ionization energy. What that means is potassium has its weakest attraction for its electrons. The highest one is magnesium, okay? So magnesium has its strongest attraction for its electrons, okay? So, on 7a, it says, describe the periodic trend of the ionization energy of the elements within a group. So here's what you've got to do. You're talking about a group, right? You're talking about a group. So Carter, when I'm talking about a group, am I talking vertical stack of elements or a horizontal stack of elements?
Vertical.
Let me give you a visual. Groups go up and down. Periods go across. Okay, there's a visual. Okay, groups go up and down. So you're going to look at elements within the same group. This is where you have to use your periodic table. Oh, look, which of those are in the same groups? Oh, that's sodium and potassium. Okay, what's the trend? Then on question B it says, describe the periodic trend across a period. Okay, well look at the ones that are in the same period going across. Okay, so that's what you want to look at. Okay, now when you get to question number 8, okay, so this is where you have to tie some things together. So you're going to be comparing magnesium, potassium, and sodium, and you want to rank them in their expected activity from most to least reactive, okay? So you want the element that's going to be most reactive listed first, and the element that's least reactive listed third. So in other words, when you react this stuff with water, which one of these is going to do you think is going to react most? Let's say, for example, with that, which one do you think is going to react least? Okay. And then on number 9, part B, which alkaline earth metal formed the most precipitate, the fewest? There you go. It's just most and fewest. So right now, I'm going to just go ahead and finish this up. You get that done, this is gonna be due on Monday. I was gonna start at the other lab, but we'll just save all of that for Monday, cause I got so many people that are gone. So all you have to do is just finish up this lab. Got it? Good? Grand? Okay. So, stop you on the camera.